This is the basic t-test. This is the simplest possible example for a hypothesis test. We consider multiple regression, but we are interested in testing the first coefficient. And h is just a known constant, like h may be 0 in your significance test for a coefficient. And we use this standard notation. And let's see what we can do here, right? The idea of the test is the difference between beta hat 1 and h, right? So both are available, right? You calculate beta 1 hat and your belief, your hypothesis has h. So the difference, how you define and how you standardize the difference is just the main implementation procedure, right? Let me then think about this first. The unrestricted model is so simple, right? Regardless of the hypothesis, you can estimate beta u and hat. It's minimizing the OLS, right? Nothing special. Okay, so you are going to get the OLS, and then I will just write down the asymptotic result. We know it converges to normal distribution with variance v, where v takes the form of this. Okay, so that is the variance. Now we are particularly interested in the first component of beta. So beta hat n can be written as beta 1 hat and beta 2 hat, or then how can you write this? Beta 1 hat is a matrix times total vector. The first component of a vector can be written as 1, 0, 0, 0, 0, 0 times the full vector. It is pretty simple. There are k minus 1 zeros. It is k by 1 vector, but when you multiply this, it becomes just 1 by 1 scalar, right? That means we are interested in beta 1 hat minus beta 1 0, and this can be written as square root n times r times beta hat n minus r times beta 0. Okay, so this is k by 1, this is k by 1, and r is 1 by k, r is 1 by k. Okay, so that means it is r times square root n times beta hat minus beta 0. So we know the distribution of the inside. Okay, that means you can apply the continuous mapping theorem, and we have r times v times r transpose. This is the new variance for linear combination of vector. By the way, in our case, r v r transpose is pretty simple. It can be written as the first 1,1 element of the variance matrix, right? Pretty straightforward, and it is also very intuitive. Okay, now then, I'm going to think about something interesting. So, what happens if, what happens to this guy, right? So the reason is this is unobserved. It is purely theoretical derivation, assuming that there is a truth like this, right? But we don't know where the truth is. But so it is, we cannot calculate this guy. But what we can do is to calculate this. So let's see this. It is, so I'll first assume if H0 is correct. If the null hypothesis is correct, then it equals this, okay? Because null hypothesis is H equals beta 1 0. So we have the same limit distribution. So this is the null distribution because we assumed the null hypothesis is correct. But what happens if H0 is wrong? Then what we calculate can be written as beta 1, 0. This is what we know, and beta 1, 0 minus H. So we are writing it this way, and that means the first part will be normal distribution 0, V, 1, 1 plus OP1. It converges to here. But the second part is, I will just call this, let's call this guy equals to delta, which is not 0, square n times delta. Okay, so then in the limit, it is going to plus or minus, so it depends on sign of beta delta times infinity, right? If delta is negative, it will, so regardless of the normal distribution, this will go to minus infinity. If delta is positive, this will go to positive infinity. So in any ways, it will converge to plus or minus infinity depending on the direction of this error. Okay, so that means it also justifies our approach. So the idea is the result, the difference, if the difference is too large, then we are going to reject H0. So the large means it can be large from large to the positive side or to the negative side, right? So this is the just intuitive rejection rule, which is pretty intuitive, literally. So then how can we do that? Our rejection rule is based on, so like too large means mathematically, we are going to find a critical value C, so that so the distance, the difference is greater than C, then you reject. But then how can we choose this C? We have to utilize probability of rejection should be alpha if H0 is correct. Okay, that is type 1 error, and we regulate type 1 error equal to alpha probability. Okay, this is the significance level. Okay, so then we have to utilize statistical knowledge to find out this probability equaling to alpha, right? In the old school textbook, we learned t statistic as an exact distribution of this guy, but we are not going to do that. What we are going to utilize here is if you have a consistent estimator for V11, then we know V11 divided by square root n converges to normal 0, 1. Okay, so we know this, and because V11 head is consistent, you may just replace that like this, right? So this is exactly the t distribution, all right? This simple t distribution, so we are going to find critical value C from the limit distribution approximately. So that means we are going to have plus C minus C. So the difference is, so I will interpret this as this is the difference, but it is standardized. So the standardized difference must be close enough to 0, must be originally 0 if your hypothesis is correct. If your hypothesis is correct, it will be close to 0. But if it may be too large by chance, it may be too large. But what I want here is this probability, the bell curve, the probability outside plus minus critical value should be alpha, right? That is the 5%, for example. That is how much I allow. By the way, significance level is 1 minus alpha. Sorry about that. Like when we say 95 percentile, like 95% significance level, then alpha is 5%. Okay, I'm sorry about that. So in this case, then this probability is alpha over 2. This is alpha over 2. So due to the symmetry of normal distribution, we have to have alpha over 2 on each side. That implies we usually write C as Z subscript alpha over 2. The definition of Z alpha over 2 is 1 minus alpha over 2 quantile of standard normal distribution. In other words, it is probability of standard normal distribution less than Z alpha over 2 should be 1 minus alpha over 2. So this you can calculate this from normal distribution. For example, when you have 5% error probability, type 1 error probability, it is 1.96. Approximately like plus minus 2 is the the idea. This is the t-test using central limit theorem. But the problem here is the idea is about the distance, right? Our idea is based on the distance of this guy, but we cannot generalize it to multiple dimension because, right? So distance is, of course, in scalar, you are going to use the absolute value, but absolute value cannot be generalized, right? But instead, you have to understand this as square root of square, right? You may think it's weird, but this is right. This is how you generalize it, right? Because you may then, like, the absolute value itself is not generalizable, but the right hand side can be generalized to, like, say, beta 1 h1 beta 2 minus h2 in this way. So this is how we generalize the distance to from one dimension to multiple dimension. So the t-test based on the standard normal distribution is not applicable when you have multiple dimension. That is, you want to use the chi-square distribution, right? Remember, x transpose, like, so if x follows normal distribution 0 omega, then x transpose omega inverse x follows chi-square rank of omega, right? That is the definition of chi-square. So in our case, square root n of beta 1 hat minus h converges to normal distribution 0 v11. Okay, so then following the rule, this implies square root n times beta 1 hat minus h transpose v11 inverse, same thing, square root n beta 1 hat minus h will be converging to chi-square 1. It's scalar. So it is scalar, so the left-hand side is simply n times beta 1 and beta hat 1 minus h squared divided by v11. That's right, right? This is going to chi-square 1. There is no difference. Instead of using this, I'm going to use its square, right? This is going to square, but basically they are equivalent. Just the details are different. Implementation is different. Chi-square is always positive. I didn't make. So this is going to 1 if h here is right. Right? It's important. You have to make sure it is true only when h here is right. If h here is wrong, also it is easy to show that I will define this as, say, w. W will go to infinity, right? By the same logic. It is following, because w will be like square root n times delta plus something plus normal distribution, but its square will go to positive infinity. So when h here is wrong, w will go to infinity. So anyhow, if h here is true, your distance, standardized chi-square distance w will be distributed this way, and I'm going to find critical value in here so that this is the rejection rule, rejection region. Reject h0 if it's beyond c, So and the probability must be alpha, right? So you have to find C such that chi-square 1 less than greater than C should be alpha. So that is, in other words, C is 1 minus alpha quantile of chi-square distribution. That's how we implement chi-square distribution. And as I said, this chi-square test is applicable to multiple dimension too.